Marius Dadarlat from Purdue. We'll talk about obstructions to group stability with respect to the operator norm.
Thank you very much for the invitation. Greatly appreciate it. Yes, so I was asked to give an introductory talk to group stability with respect to operator norm. I make an effort, but looking at the slide, I don't know if I succeeded to make it. Oh. All right, so let's revisit the definition because I will change a little bit the terminology. So I would say that for a countable discrete group, gamma is local to local stable with respect to the operator norm. The term matricially stable is also used if for any sequence of unital maps to unitary groups in matrices UN, which is asymptotically multiplicative, there is a sequence of two representations which approximate pointwise the given maps. Okay, so that we start with asymptotic multiplicativity pointwise, and we want to approximate pointwise, hence local to local stability. All right, but we have seen talks where, like Alex Lubovsky, where the defect to multiplicativity was measured uniformly. And such, I will call such stability only for today, uniform to uniform stability. And for a reason that will become apparent in a second. So, there are several natural stability properties that one could consider. For a sequence of unital maps, we ask, is there a sequence of true representations such that, yes, see, if we assume uniform multiplicativity, do have a uniform approximation by representation. So this would be Coulomb stability, but I call this uniform to uniform stability. Here, down here, it's local to local stability. Then one may ask, what if we impose this uniform approximate multiplicativity but ask just for local approximation by representations? And this would be uniform to local stability. And of course, there is another arrow which I did not draw because then the diagram becomes even more complicated. But in that case, we know the answer. So gamma would be local to uniform stable if and only if it's finite. So in some sense, it's not interesting. Okay, so I hope that that terminology will help us to describe the question. Although I will focus mostly for local to local and uniform to local stability. Okay, now, very few groups are known to be matricially stable. That is local to local stable. It's a very strong condition with respect to norm. And it's hard to trace the history of the subject. Probably for finite groups, I mean, it's very likely, and for Z, this goes back to Glim if not before him. But I want to make one point here about the role of C-star algebras in this context, right? So if you have a group or just any set, right, you construct a vector space. If G is a group, this is the group algebra, so it becomes a ring, right? This is a ring, okay? So now, if you want to do some analysis, especially spectral theory or maybe define invariants which are homotopy invariants, but just spectral theory, you need obviously to complete the group ring with respect to some norm. And there are several ways. You can go to L1 gamma, or for better spectral theory, or not better anyway, to C star gamma. So you make that a C star algebra. So this is a universal object which is very complicated and hard to handle typically, right? But it has this universal property that whenever you have a homomorphism from gamma to the unitary group of a Hilbert space, or more generally to a C star algebra, so every such representation extends uniquely and corresponds to a representation to morphisms of C star algebras. Now, here you can do spectral theory and then define homotopy invariants. You have K theory and other topological invariants associated to groups. So that's sometimes it's a useful viewpoint. So that's one reason to talk about C star algebras in connection with norm stability, operator norm stability. Now, what happens if, for instance, is gamma is finite? Just to illustrate, right? Now, how is this algebra constructed? One way is to take all irreducible unitary representation of all Hilbert spaces and take their direct sum. So for a finite group, we have finitely many irreducible representations. Each irreducible, bit irreducible, has nothing in the commutant, so its image consists of full matrices. So because of that, the C star algebra of gamma is direct sum of finitely many matrices. So I have the complex numbers for the trivial representation plus some other summands depending on the group. Okay, so you see this is, in this case, we'll remember very little about the group, of course. But if you care about norm stability, right, which the way that Alex put it, it's a lifting problem of a group homomorphism. But then by universality, it's the same thing as a lifting problem for a star homomorphism. So now, instead of trying to lift a map out of the group, is the same thing as lifting a map out of this direct sum of matrices. And this reduces to lifting projections and unitaries, or partial isometry matrix units, but ultimately unitaries. So that would be a C star algebraic point of view in which one can show, that finite groups are local to local stable, but initially stable. Now, of course, the lifting properties is very restricted in norm. There are all kinds of obstructions. And in the paper of Eilers, Schulman, Sorensen, they studied torsion-free finitely generated virtually abelian groups, so crystallographic groups, and they established that such a group is matricially stable, local to local stable, if and only if the rank is at most 2. It can be rank 2, but then the rational 2 cohomology has to vanish. And the proof is quite difficult because their proof is not by lifting group relations, but going to a C star algebra, which is sub-homogeneous over a space. Probably Soren will talk more about it.
Both directions are difficult.
No.
If
Both
the answer
directions.
says 3 and more,
One of them, it's more difficult, showing stability. The obstruction is not obvious. I mean, it's not hard, but still, it goes through K-theory. Reduces essentially to the non-stability of Z square, and to Voiculescu's examples. You restrict the almost representation to a suitable subquotients, and then you find the sister algebra of Z2.
They have torsion, right? Some of the crystallographics group.
Oh, for torsion free, there is less for torsion free.
We study all of them.
Okay, so then I forgot. Well, anyway. And then virtually, 5D virtual free group, for instance, SL2 are matricially stable. Okay, and then Gerasimov and Shchepin, they establish matricial, that this local-to-local stability is closed under amalgamated free products and H and N extensions over finite groups. Essentially, that's all we know. Maybe there are a few more examples, but so it's very hard. Okay, so it's hard for several reasons. So, what if you don't want to perturb, but you allowed some flexibility in the sense that it's okay to perturb after you take direct sum with a representation? Then there are more examples, and the answer, at least in the minimal case, and there are the generalization, and then one can give decent answers using K-theory. But that I will not address. Okay, so now let's revisit just the classic example, Kazhdan and Voiculescu. They really show that Z squared is not matricially stable, and I will comment on the contribution. Okay, so you have seen in Tamar the examples coming from a irreducible representation of the Heisenberg group. Okay, so I'll go faster about it. So the commutant is small, and the property is that expressing that Z squared is not local to local stable, you cannot approximate these almost commuting unitaries by commuting unitaries. Okay, now in Kazhdan's paper, he states this for surface group of genus at least 2, but implicit in the proof, he shows the case of Z squared, because the argument applies there. And okay, Voiculescu used a Fredholm index argument, and that's very relevant, you know, as you'll see. Whereas Kazhdan used a winding number, okay, which his argument in the case of Z squared reduces to the winding number argument that Itamar presented, but he wrote that in the form, okay, oops, all right, sorry, I don't know how did, what I did here. Okay, sorry. Oh man. I have to scroll back, so I think I pressed home or something here. Yeah.
I think if you use the arrows on top, it should work.
Yeah, so I'm giving you presentations. Okay, and then I'll go back. Okay, so this is see, this is the invariant that Kazhdan used. Or for genus G, there are several such products corresponding to the generators of the surface group. But this is exactly the winding number of this loop. So the winding argument was implicit already used by Kazhdan. Okay, so this was rediscovered by Excel and Loring. Okay, but what Kazhdan showed, he stated that surface groups are not Ulam stable, uniform to uniform stable. But since he used this winding argument, he proved, in fact, more. In fact, he proved that, so Kazhdan proved that this group is not even uniform to local stable. So it's a very strong instability. Okay, and that's one thing that I wanted to understand. I will address that in the book. Hence, the third arrow, the third kind of stability. All right, so MF group. So first I would state an older result that I had. So recall that a group, it's MF, not its histile algebra, the group. If it embeds in the this product of unitary groups divided by the subgroup of infinitesimal in this case, so un minus 1 goes to 0. And since we know that by Tikuisis, White-Winter, that amenable groups are MF, then one can deduce immediately, rather easily, that the groups which are locally embeddable in amenable groups are MF. So this is a large class, but there are also other groups. For instance, the group that Andreas Thom introduced, that was hyperlinear, but not LEA, the same group, it's MF, not only hyperlinear, by a similar argument. Okay, so now this is a theorem that I had. So let gamma be an MF group that has a gamma element. Okay, so that's a KK theory conditions, and I will discuss certain geometric conditions which imply that. Okay, so MF group, I explain what MF group is, and that has a gamma element. We'll give example. So if at least one of the even rational cohomology groups does not vanish in some positive dimension, then gamma is not local stable. And this applies to amenable groups, to linear groups, to hyperbolic groups which are residually finite. And what I wrote there is that inclusion, they are both an MF and have gamma elements. Although the proof that they have gamma elements, those proofs are major results by other people. So, yeah, so okay, and then you may ask, okay, what is known about linear groups? And that made Lubotsky, Sauer, and Einberger in 2023 showed that lattices in semi-simple linear groups, well, at least co-compact lattices, are not local to local stable. In fact, they showed that at least one of the even homology, rational even homology, is not trivial. In all cases, unless the group is locally isomorphic to this Lorentz group of SL3R, and in those cases, they also have detailed results about the situation that most groups satisfy this property. That's it. Okay, so this will be a first set of examples. All right. Now, about the gamma element. Okay, so I'll just show 1 second the definition of having a gamma element. And with one comment, but this is a sufficient condition.
Marius, maybe
yes.
Just
yes.
can you put the stuff? Yeah. I want to mention, because we tried a lot to do it also for p-adic groups, and there we don't know, because if the dimension of the Boatitz building is even, then there is a non-zero cohomology. But if the dimension of the building is odd, all the even cohomology vanish. And for proving this, we only knew to use your criterion, and we were kind of stuck on that problem for a long time. I mean, do you have maybe some more criterions to help us?
Well, I have a conjecture. It's unofficial, the group. I believe that, let's say the group was torsion free. I really believe that its geometric dimension should be small. Big gamma should have a realization as at most dimension 2 space.
At most dimension?
2.
Wow.
That's based on what happens to virtually a billion and some other, but it's speculative. All right, so I'm mentioning coarse embeddability in Hilbert space. Okay, and you'll see in a second. So this is a notion due to Gromov, and I wrote the definition. A map is a coarse embedding if the distortion, if the distances are not excessively distorted. Okay, so a group, we call its coarse embeddable in a Hilbert space if its Cayley graph is coarsely embeddable in a Hilbert space in the sense of the previous definition. And now, intuitively can be drawn in H without excessive distortion. And the classic example, I mean, you know, it's the free group where you draw the tree, and every time you ramify, you go in a new dimension orthogonally. So there is no distortion. And okay, so this has a long history, but this is how this is relevant based on the idea of Kasparov and then in full generality Jean-Louis II. Groups which are quasi-embeddable in a Hilbert space admit a gamma element. And that's the second assumption of the theorem. I have two conditions, MF, and now a weaker condition would be that the Cayley graph embeds. And okay, so maybe I'm diverting the discussion. Okay, so this is what it means to have a gamma element for the locally compact group, but it's technical, it's an abstraction of this technique, Dirac, dual Dirac, that Kasparov employed and was generalized in various contexts, but we don't need this. All right, and
maybe can you say just how, so cohomology, we know a bit how it contributes to non-stability, but can you say a bit why this coarse embedding or some kind of geometric property, how is it related to, how does it give an obstruction to stability?
No, it has nothing to do with stability. It's so there is, right, to a group, I'll start, this works for the non-discrete groups, right? We have two objects, which you may like or not, and the reduced system algebra generated by the left regular representation, right? But we also have the classifying space, and then Kasparov proved the first result, showing that these objects are dual, satisfy, loosely speaking, some sort of Poincaré duality, and that's the content of Baum-Kohn conjecture. So the K theory of this is related to the K homology of this, and the other way around. And that there is a map which I described in which goes from the K homology of this to the K theory of this, which will be Kasparov proof that it's surjective if we have a gamma element. So what we'll do, I will explain, we'll transfer Elmos representation here to bundles here using this co-assembly map of Kasparov, which on compact subspaces admits a complete description, which I will explain. So that's the role of gamma element, of proving having results in the direction. Well, I contributed nothing to that general theorem, but I'm using it. But before I explain some of those methods, I will address again the stability that I like, uniform to local stability. Right? So I repeat the definition. Uniform, almost multiplicative, we require just local perturbations. Okay? And we have seen that this was done in Kazdan's paper, and his quasi-representation he constructs are projective representation, and he's using a bounded two co-cycle. Okay, now the result of Burger, Berger, Ozawa, and Tom, they prove that such groups are very general, hyperbolic, non-elementary, are not Ulam stable, but those exponential maps, those almost homomorphisms, they perturb locally to true homomorphism by compactness of the circle. In fact, this has to do, loosely speaking, not with the kernel of the comparison map, but with the image of the comparison map. And I will...
I understand. So you assume you have, like the way I said it yesterday, that the kernel from the bounded cohomology to the ordinate cohomology is non-trivial.
Yes.
So this means that you have bounded to co-cycle, which are not co-boundaries. Does this automatically implies that you are not uniform to local stable? This is stronger than what I said on what Burger and Java and Prof.
So we have the comparison map, right? It's equivalent, so no. Okay. So if the kernel is non-empty, one has quasi-character and the construction that you explained. Now, if you take something in the image, this is take an element which survives here, then with Forrest Levy, we check that they are not uniform to local stable, but with respect to threshold C-star algebras, and depending on favorable circumstances, we can tell for certain groups that they are not uniform to local stable, but not in full generality. But I'm still interested also in higher dimensions, not only to homology, and that's why I will revisit this in a special case. And in fact, this is developing an idea of Gromov. Okay, then I verify the following. So if M is a close connected Riemannian manifold with pinch negative sectional curvature, so this means that the sectional curvature is negative at each point, since the manifold is compact. Now, the group, of course, it's hyperbolic, but still, now we assume that it has to be residually finite. And then again, if one of the cohomology group does not vanish in some dimension, then gamma is not uniform to local stable. And so, for instance, if we take the manifold to be this homogeneous space associated to the action. No, it's a space associated to the action of the lattice in a Lorentz group, acting on the n-dimensional hyperbolic space that has constant sectional curvature -1. Okay, so in even dimension, that manifold is orientable, so top cohomology is non-zero, and then if n is odd by Poincaré duality, we have to assume that one of the homology groups it's not zero. Okay, and then this includes the example of Kazdan, but you might have higher invariance out of which one you construct uniform to local unstable groups. Okay, and then you may ask, okay, what happens in the odd case? Again, Bader, Lubowski, Sauer, and Weinberger studied this, and they show there are plenty of lattices which satisfy the condition, and they prove this in particular to show that you don't have local to local stability in this case. But then if I invoke the result before, for instance, in this case, a group as above is not even uniform to local stable. Right, so maybe I'll read the result there. So if you start with an arithmetic, the result is more general. This is only part of the result. If you start with an arithmetic whole compact lattice in that Lorentz group, in dimension, you need SO larger than 7. Then there is a finite index group such that all its finite index subgroups satisfy that. So there are lots of them. All right, and just to discuss this, to close this overview, right? So we had three notions of stability, and I put here a table which summarizes some of the things that are known. Okay, so the Ulam stable groups and the matricially stable groups, they have non-empty intersection, which is quite small. And we know from Alex Tops that most higher rank lattices are Ulam stable and amenable groups. Okay, then I put there an example that shows that there are groups which are uniform into local stable, but are neither local to local or uniform to uniform, and that uses the combination of the techniques that are known from these examples. And now, what if we look at rank 1 lattices, right, which will complement this class? For many of them, by that theorem that I presented, they are not uniform to local stable. All right, so now to this basic question. How to construct non-trivial quasi-representation or almost representations? I'm using the term interchangeable. I like almost representation because they go well with almost flat bundles. But then many people use the term quasi-representation, including myself. Some of my papers I use quasi-representation, some other almost representations. So. Okay, and there are two methods. One goes back to Gromov, and then he constructs almost flat bundle over big gamma in general, but over manifolds, which are almost flat, and then they have a connection with small curvature, and then parallel transport will give rise to almost representations. And if the vector bundle is not trivial, then it's not flat, then the corresponding almost representation, it's not close to a representation. Initially they made an announcement, and then they wanted to prove at the time all known cases 91 of the Novikov conjecture by this method, but then they found a better method for the general what they wanted to prove. And then the other method, in fact, that Novikov. Right. And the other method that I employ is to use known results on the Novikov and Baum-Combe conjecture in conjunction with finite dimensional approximation properties of group C-star algebra, such as quasi-diagonality, and use this to produce interesting approximate representations. Okay, and perhaps I'm a bit short of time. I'll advertise in the abstract that I will focus more on the the functional analytic method, but I might say something. I will say something about the other method because that's essential. That's the only way, following ideas of Gromos, in which I can one can exhibit this uniform almost representation, which are cannot be perturbed representations. All right. So now I will explain a bit. All right. So at Segal, at initially for finite groups, if you have a representation, you can associate a flat bundle on the classifying space. And that extends to the group ring. And then, following an idea of Kasparov, they extended this method to Fellum representations, right? So what do you do if a group is not compact, has very few finite-dimensional representation, you don't have a group ring. And then Kasparov proposed KK gamma CC. So it's a ring, and it's a good substitute for the group ring. All right. Now, on B gamma, okay, so EG is E gamma there. And we have the Mischenko flat line bundle, so the fiber, you can take the fiber to be the group algebra or L1 gamma or C star gamma. So gamma acts diagonally on the classifying space and on the C star algebra. You see? So that these are the two objects which are mostly in duality. Classifying space, group ring with some completion. And there is like a Poincaré duality element which induces this. You might speculate this maybe this Mischenko line bundle plays that role. All right, now I assume for simplicity that B gamma is compact. Otherwise, one has to work on various subspaces of B gamma using an exhaustion by larger and larger compact spaces. So I will assume. Now, what does it mean that the bundle is flat? Is that transition maps are constant, and in fact, transition maps are given by group elements. So here is there are the elements Sij. Eij are matrix units, Chi a partition of unity. So you see, so here the image of this idempotent corresponds to the sections in this, continuous sections in this bundle, right? It's like a Swan's theorem, right? But how do I construct this projection? You know, so the formula looks complicated, but just look at this first matrix. What is the Ij entry? I have the partition of unity, Chi, Kj, and Sij, the cocycle. So see, it's a matrix of size, the cardinality of the cover, and those are the entries. Okay, so why is it an idempotent? Well, partition of unity and the cocycle condition. So that's an idempotent. Now, if you have an idempotent in the matrices over an algebra, now if you have an almost representation of that algebra, you can apply the representation amplified. If it was a representation, the image of a projection, it's a projection. It's an almost representation, the image of a projection would be almost a projection. But then, if you are in a C-star algebra or an algebra with good spectral theory, you can perturb that almost projection to a projection. And therefore, that's the vector bundle that one would associate to an almost representation. Okay, and you see, it's like I take that matrix and I apply the almost representation of the group entry-wise, and I get an almost projection. On the next slide, I repeat that. Okay, so it's an almost a projection. We perturb to a true projection, which corresponds to the section in a bundle. I call it almost flat So we don't need yet the definition of almost flat. A flat bundle, it's a bundle where the transition functions are constant. An almost flat bundle, it's a bundle where the transition function with respect to fixed cover are almost constant. Why is there a huge difference between them? Let's say we are on a manifold initially, but it's more general. So if the bundle is almost flat, you are on a flat on a manifold. So Milnor pointed out that by Chen while the curvature is 0, and therefore the rational Chen classes vanishes. Whereas if for an almost flat bundle, that's no longer true in general, assuming that you can construct such almost flat bundle. Right? So then if you can find almost representations for which the associated bundle has non-trivial Chen classes, rational Chen classes, then you cannot perturb the almost representation to the representation, because if you could, the bundle that you have will be isomorphic to a flat bundle, and that would be the contradiction. So that's the obstruction that I use. Now, so here I'll just mention.
Sorry, Marius?
Yes.
Can you just repeat what is Sij in the previous slide?
Yes, Sij are group elements.
And how do you pick them? Like, what is the relation between the partition of unity and the group element?
You choose a partition of unity, ideally with connected, where the vector bundle is trivial. And this Mishenkov bundle, it's flat, because it comes from action of gamma. So if you identify the transition maps coming from the trivialization, they are just multiplication by a group element. And they are automatically a cocycle. Yeah, so that doesn't matter how you choose, because if you take almost delta, it's not enough, and then. But you see, if you have a bundle given, it's very difficult to compute this characteristic classes, right? Except for the first Chen class, there is no combinatorial formula. There are some, but they are very complicated. Okay, and moreover, ideally, you would like to have at least a first obstruction which you can compute easily and explicitly, and this is what I worked out with Forrest, Levy, you know, based on some previous papers. So now you see this expression that you've seen in Kashdan. Rho A, rho B, rho AB inverse, it's something very close to 1. You can take logarithm. Okay, and then the trace. This is the real number, but one can check. You see, I regard this as a map on gamma, and this satisfies the two cocycle equation. Okay, so if big gamma was compact, you know, then defines a global class, but in general it's only local. So, but still it satisfies the equation. And then, okay, then how do you know that such a thing it's non-zero or not, or when? One easy way is to take Kronecker, pair it with homology classes. Okay, and then if you take that, I have it's a very special index theorem that shows that the values are integers, and what you get are exactly the winding numbers from Voiculescu's paper and Kashdan paper. So those winding numbers are pairing between this first Chen class and homology classes, the fundamental class of the two torus or of the surface group. Okay, so if you have a bundle, that's the first test, but we have seen that by the higher dimensional obstructions, and of course they are. So other Chen classes we cannot compute only if the representation is also projective, and then we have other results. But I would. Okay, and then I mentioned this thing with homology classes that you obtain. Okay, the rest I explained why this is an obstruction, right? So the difference between almost representation or representation was translated by this push forward to a difference between almost flat bundle and flat bundles, and which you distinguish by using Chern classes. If you can, so, but then all right. Now, the question is, all right, but how do we know in general that we have enough almost representations? Ideally, you'd like to have so many almost representations that this push forward, that this bundles is a rho, exhaust all the K-theory of big gamma. So you want to realize all the K-theory of big gamma by almost flat bundles. Let's assume that it's possible, right? Now, if you assume that the group is stable, you perturb almost representation to a representation, and then you deduce that the K-theory of big gamma is generated by flat bundles. But Chern character gives an isomorphism from the K-theory of big gamma to even cohomology. Rational, so the cohomology also has to be rationally trivial. Hence the statement that I gave. But that relies on this method. Can you produce enough almost representation so that they push forward? Pushing forward, you get all K-theory of big gamma. So, in other words, what to say, is the K0 of big gamma almost flat? Okay? And there are two ways of approaching this. For certain manifold, there is this method of gamma, and then I will say a few words about the method that I introduced. So, construction of non-trivial quasi-representation.
Excuse me?
Yes.
Are there known examples of groups, let's say infinite groups, where the K0 of big gamma is flat, is generated by flat bundles? No. Oh, yeah?
Yeah.
Yeah, for example?
It's a crystallographic graph, I think.
Ah, okay.
Okay, so this is along this. So it's known that, so if you have a characteristic class, if it comes from a flat bundle, it has to be torsion. So this is a difficult question. Which cohomology classes are characteristic classes of flat bundles? So this is known in dimension 2 that everything comes from flat bundles. So then you can construct some examples along those lines. But in some sense, that's the point, right? The difference between almost representation and this philosophical representation is this difference between almost flat K-theory, which for many groups is everything, and flat K-theory. Okay, maybe I'll skip ahead. All right, so Kasparov generalized this map of Atiak-Segal, which goes from the group ring to vector bundles. Okay, and the group ring corresponds to the K homology of C star gamma here. All right, so that's complicated. That involves Kasparov product, and I'll take a baby example to illustrate how we can adjust that. Okay. Now, what is this K homology? This is also KK C star gamma G. Consists of pairs of representations. They are not unital, they hit various, such that their difference is compact. Right, so here you can see how this generalizes the group ring, where you take differences of finite dimensional representation. So this is like a Fredholm analog. So the key technique is to introduce a subgroup of this, where the second representation it's block diagonal, or more generally quasi-diagonal. But you can imagine it's phi prime, it's a representation which is direct sum of finite dimensional representation. And that works well, for instance, for residually finite groups. That's what you take. And for groups satisfying the assumptions that I mentioned, if you restrict this co-assembly map to this subgroup, the map is still rationally subjective. Yes?
If phi prime is quasi-diagonal, then any compact perturbation is quasi-diagonal?
Yes. Right. Okay, so now, I'll be a bit vague here. You have two representations with compact difference. You have two representations with compact difference. The second one is block diagonal. So you can find a sequence of finite dimensional projection, larger and larger, which commutes perfectly with the second one. You respect the blocks. And therefore, it commutes up to the compacts, but the error goes to 0 with the first one. So all you have to do is to compress these representations to finite dimensional subspaces of H, and this diagonality condition helps. And then if you have those two compressions, those are the non-trivial quasi-representation that we are seeking. In fact, the second one is a true representation in this case. Only. Okay, and how do I know that that's trivial? Then one shows that in this case, if you restrict to compact subspaces, or if B gamma is compact, one can describe the image of this co-assembly map as using the push forward that I mentioned before. Remember, Mischenko line bundle, you push forward to an almost representation. You see, so one can describe this map. So those are the quasi-representation, and then the image of this is the same as the image of Kasparov map. I really want to write. Okay, so I'll one thing. So you see, let me say that gamma was the complex. Gamma is a point. So in this case, the co-assembly map would be from KKCC to K0 of a point. You know, I mean, this is the integer vector spaces, right? Now, what is the assembly map doing? So you see here, if I follow through, if I'm looking at phi of 1 and psi of 1, those are projections. So I have two projections on an infinite dimensional Hilbert space such that E, okay, let me put E minus F, they are compact. Okay? So I have two projections on a Hilbert space with compact difference. You see, that's the description of KKG, but you have representation of the gamma instead of a representation of a point. Now, how do you associate with this an integer? Right? So, the general method is this. You look at the Fredholm FE, it's a Fredholm operator from EH to FH, it's Fredholm, and you take the index. And you get the integers, right? But that's not what we want to do. What I'm doing there is that, you see, if those projections were finite dimensional, this is automatic, so the integer would be the dimension of the first one minus the dimension of the second one. Okay? Can I somewhat do something similarly? Yes. So all I have to do is to find a sequence of projections which go to 1 and which commute with the second projection. You know, I take an orthonormal basis that respects F, so, and therefore Pn will commute asymptotically with the first one. So now I'm looking at Pn, Epn, this is almost a projection, and then Fn, Pn, Fn, Pn, that's a projection. This is almost projection. And I perturb it. This is a finite rank operator. I perturb it a little bit, and I get a true finite dimensional projection. Finite dimensional projection, the difference of their rank is the Fredholm index. So this is how you localize the Fredholm index. And this is this construction instead of doing it with projections. And here, hiddenly, I'm using that the system algebra of a point, it's residually finite. One does that for you. All right, so I'm running late, so maybe I'll skip ahead. Okay, so I'm finished with this. Okay, I repeated the argument. We also have a stable uniqueness in the mutable case, namely, if two almost representations have the same bundle, isomorphic bundles associated, are they related to each other? Yes, after we add finite dimensional representations. And their generalizations due to Rufus-Wheeler to non-mutable groups, including surface groups. All right, I don't have time for Gromov, but for Gromov methods, sure, I apologize. But this illustrates parallel transport on the sphere. Okay, so you move a vector parallel along geodesics, and then parallel transport. Okay, if the connection is compatible with symmetric, you get a unitary representation. But you see, you don't get. It's not a representation. You don't get back, and the error depends on the curvature and the area of the homotopy. If you work on the manifolds that I discussed, the area of any geodesic triangle in the universal cover is always less than the curvature, absolute value, times pi. So therefore, the error is area of homotopy small, curvature is small for almost flatness. So therefore, parallel transport gives us an almost representation, which it's a global representation. Why is it global? Because all geodesic triangles have bounded area. So that's the argument essentially for the second argument. Thank you.
Any questions for Marius? So using this Gromov method of constructing almost flat bundles and the approximate monodromy of those bundles, like constructing an almost representation out of this, is this I don't know, even for three-dimensional hyperbolic space, does this give explicit almost representations?
No.
Like you cannot compute this parallel transport somehow?
I never tried, but it looks difficult. No, I don't have
but
the
it's
background.
more explicit compared to the KK theoretic methods?
Yes. but here you have to produce first bundles. But Gromov pulls back bundles from spheres through small. But that is not that explicit either. So. Yes.
How essential do you think it is to have the gamma element? Is there any way to?
Then one doesn't have subjectivity. So then, if one compresses these KK elements, right, you don't know what you get in the range by push forward. Yeah. So that depends on the subjectivity of this.
But I mean, okay. So the question is, do you actually need subjectivity? Because I mean, you might need.
No, for proving instability. But if you have subjectivity, that you know that the homology vanishes. That's why I need subjectivity.
Can you repeat this example? So Like this is for which kind of group this would be or relevant, or for which kind of element?
Not the sphere.
Yeah, obviously not. So.
So I take a manifold, compact, let's say orientable, even dimensional, with a strictly negative curvature.
I thought you want I thought the point here is that you want positive curvature.
No, negative, negative.
Ah, this was to show. Okay, this is.
This was to illustrate how the area of the homotopy impacts parallel transport.
Okay.
You see big area, big travel, you see the yellow arrow, instead of coming back, coincided with the red arrow, that will correspond. This path will correspond to group elements. Right, and you get an error which...
So you need negative curvature to really construct the almost representation.
Uniform almost representation.
Yes, come on.
Because if I know just local almost representation, the functional analytic method, I think it's more powerful, at least, as far as I'm concerned.
Okay, so let's thank Marius again.